All right. So, so we're recording. We're live. Lecture 15 in structural analysis. We're going to be talking about concentrated moments today. And since we're talking about concentrated moments, that means we can finally start to do a moment diagram for a cantilevered beam. So we'll do that today as well. Same old pattern with the homeworks. We've graded homework 4.3. Homework 4.4 is due today, and homework 4.5 will be assigned today. And so we'll keep on trucking with that. If you look here on the homework schedule, we're going to have a homework due Wednesday and a homework due Friday. After that Friday homework, I'm not going to have any homework assigned until after the exam. So I'm not going to make you have anything due Monday and Wednesday because I want you to spend that time studying for the exam. Okay. You had a question, Mr. Adkins.
Yes. Now, when I did the problem in Excel, now when I was trying to calculate the shear and moment values, whenever it kind of reached a zero value, it did something like a weird value to like e to the power of some value. I don't know why. And also,
Go ahead.
Sorry.
No. You go.
And the other thing is that when I was trying to do the moment diagram, I calculated the area, but there's something wrong that didn't equal to zero in the end. I found the areas, but that's about it.
Well, I don't remember the functions right off the top of my head. Give me 1 second. I want to pull something up here on the screen here. Hold on. So, give me a sec. So when you did that homework assignment, what you should have gotten is a shear function that should have looked like this. It should have been something like 18.2 minus 1 per x, and then the moment is 18.2x minus 0.7x squared. Okay. Now, when you plot that, what you should get for your shear diagram is it should just look like a line. So your shear diagram kind of looks like this. And then your moment diagram should go up and then come down. So my first question is, did they look like this?
Yes, but admittedly, I don't know what Excel was thinking, but on the shear diagram, it went straight down, and then at the 20-foot mark, it went like a triangle again. I don't know.
Then the only thing I can think of is that there's like an error with how your formula was tracking, because I mean it should just be a smooth line and a smooth parabola.
I know. I'd make sure, and the values were like perfectly equal zero at the end, but for some reason it just.
Well, the shear diagram shouldn't equal zero at the end. It should be like positive 18.2 and negative 18.2. Yeah. The moment diagram should be 0 and 0.
Okay, yeah, we're good there.
Now, let me interject one thing. Every now and then, when you're doing these types of calculations, when you get to the end, instead of 0, it'll say something like, 1 times 10 to the negative 19 or something, and that's fine. That's 0. That just happens every now and then with Excel, and that's no big deal. Did that answer your question? I mean, I'd have to look at the assignment to know any more.
Yes, I think it did.
Okay. All right. Well, let's let me hit the share button. Let's jump into concentrated moments. We have 2 examples today, but I think they're pretty straightforward. There's honestly, if you can handle what we've done for the past couple of lectures, then you should be able to handle this. There is a slight I don't know, like a slight thing you got to watch out for with the shear diagrams, but it's not bad. This is really straightforward. Okay, so we're still borrowing off of the same relationship that we've derived between load and shear and moment, and we're still borrowing off of our same graphical approach. So this is all going to hold true. Between load and shear, the slope of the shear diagram is equal to the load, and the change in shear is equal to the magnitude of the load. And then when we're looking at shear and moment, the slope of the moment diagram is equal to the shear, and then the change in moment is equal to the area of the shear diagram. And that's fine. And I have here the derivation was focused on distributed loads, but you can draw similar conclusions about concentrated loads and moments. The book, like I said, the book goes into much more detail on the derivations, and I'm happy to do it with you in here if we desperately need it. But I think, you know, in practice, like doing it in practice ends up, you can reach the conclusions a lot easier with some of these other points. Like, in other words, if you just do it, it'll make sense. And if I sit here and go through a derivation that you all already have. So let's talk about shear and moment diagrams and what happens with concentrated moments. Now, a concentrated moment is just that. It is a moment, okay? So it's not a force. So when you look at concentrated moments between the loads, there's zero force applied, so there's no change in the shear diagram at all. It's a concentrated moment. It's not a force. So when you're drawing your shear diagram, you kind of ignore the concentrated moments. They just don't matter. What's going to happen on your moment diagram, though, is you're going to get a constant jump. You know, like a concentrated force on a shear diagram causes a constant jump. You know, you suddenly go up 20 kips and then suddenly go down 5 kips or whatnot. That's how you draw a shear diagram. With a moment diagram, anytime you see a concentrated moment, it's a constant jump. So now the process is still going to be the same. We're still going to integrate the shear diagram to construct the moment diagram. That's not going to change. But what we're going to find is that the areas don't match. You remember up until now when we look at our shear diagram, you know, if we have a positive area of 450, we're going to have a negative area of 450 because the sum of moments has to be equal to 0. Well, that's not going to match this time, and the difference is going to be whatever the concentrated moment is. Okay, and so that's going to be something we need to watch, and then that's also going to affect how we deal with cantilevered beams. Now, and the reason I say that is because when you have a cantilevered beam and you have a fixed support, you have a reaction in the x direction, a reaction in the y direction, but you also have a moment reaction. And so that moment reaction is a concentrated moment. It's going to affect how we draw a moment diagram for a cantilevered beam. So I have 2 examples for you. I have this one here, and then I have a cantilevered beam here. Now, first off, with both of these examples, I've given you the reactions. We've already done these examples. I tried to reuse as many of the examples that we've done before because I want today to be focused on the shear and moment diagram. I don't want to waste time trying to compute the reactions. But the idea is you've already done this. So you can always go back in your notes and go, oh, yeah, we did this problem. And so there's how you compute the reactions. So we have an overhanging beam. We have a reaction of 15.2 kips on A, a reaction of 24.8 kips on B, and I want to draw the shear and moment diagrams for this beam. So let's take it one at a time. Let's do this example 4. So I'm going to stop the share. Let's see. Share the screen. Okay. So here's the beam. Let me go ahead and put my marker on. Turn this up. Okay. Take my keyboard off so I can write. Okay. So we're going to draw the shear and moment diagrams for this beam, and we're going to do it like we've done every problem up until now. We're going to draw the shear diagram, integrate, and then draw the moment diagram. So the first thing I'm going to do is set this up. I'm going to do it like I've done previous problems. I'm going to draw out a series of grid lines. Like I said, there's no hard and fast rule for how many of these things that you draw. I just draw enough to where I can track what's going on with the shear diagram as I draw it. Okay, let me scroll down a bit so I got a little bit more room to draw. Okay, I think that's good. Okay. So let's start this out. Okay. All right. So like I said, whenever we draw a shear diagram, nothing changes with the concentrated moment. It's still the same target. We start at 0 and we end at 0. Okay. Now, I'm going to do this problem the same way that we've done shear and moment diagrams in the past. So again, nothing's different, okay? So we're going to start at 0, and then the first thing that we do is we jump up to 15.2, okay? Now, if I jump up to 15.2, what do I do from here? Well, what do I do from A to this point right here? How much do I go down? I'm going to ask Chad. If I'm at 15.2, I'm going to go down. How much am I going to go down? And I'm going to go down. Okay, so -3. -3 is the slope. Okay, so I'm going to go down 3 kips per foot for 10 feet. So that's 30 kips. That'll put me down at -14.8. So Mr. Romans and Mr. Garrison are on the right track there. This is going to be -14.8. And I'm going to go down like this. Okay, so the slope of that line is -3. You are correct. And so it's a constant load, a linear shear diagram. Start at 15.2, go down a total of 30. Why is it 30? It's 3 kips per foot over a distance of 10 feet. So 3 times 10 is 30. And so -14.8. Okay, now from this point to B, what happens? What does it look like from this point to B? Somebody help me out.
Well, since there's no force it gets during the 15 feet, it will be a constant line.
You're exactly right. So a flat line like that. And so this point right here is also 14.8. And then I'm at 14.8. Okay, so if I'm at 14.8 and I jump up 24.8, what's that put me at? +10, exactly right. So that puts me about right here. Okay. Now, we're going to reach the same conclusion from B to this concentrated moment. It's going to be flat. Now, what do I do here? Nothing. Nothing at the moment. Nothing at the moment. I like that. Exactly right. We are doing nothing. All right, let me see. Okay. So, keep on trucking. Drop down to 0. That's exactly right. So +10, +10. So right now, we ignore that 20-foot kip moment. Okay? We ignore the moment. Okay. So, before we move on, any questions? All right. So, now what I'm going to do is I'm going to split this up into a couple of regions. Let's call this region 1, region 2, region 3, region 4, and region 5. Okay, now in order to draw the shear diagram, we're going to need to determine the areas under, in order to draw the moment diagram, we're going to need to determine the areas under the shear diagram. So let's take easy ones. Let's do 3, 4, and 5. What's the area of region 3? And then while somebody's determining the area of region 3, somebody tell me what the area of region 4 and 5 is. I'm going to save the triangles for the end.
Region 4 is 100. The same with and region 5 is 100 as well.
And region 3? So here, I'll put this on the board here so we have
-222.
Okay, so we have -222, exactly right. Okay. I keep having this dialog box pop up on my other chat over here. I'm having to come over here and fix it. I don't know what's going on. There we go. All right, so we've got -222 and +100. +100. Okay. Now, we've got this region here, this region 1 and region 2. Okay. Now, we've had problems like this before, so this is going to be hopefully a little bit of a review. Okay. We need to determine this distance, which I'll call x1, and we need to determine this distance, which I'll call x2. Now, somebody remind me, what is the slope of that diagonal line? That line going like this. What's the slope of that line? It's -3. That's right. Okay. So I propose that x1 is just 15.2 over 3, and x2 is 14.8 over 3. Now, if you chug these out, you're going to get that 15.2 over 3 is 5.067 feet. And this one is 4.933 feet. And remember that x1 plus x2 has to add up to be 10, right? Because that incurs in this region here, right? And so whatever x1 is and x2 is, it's got to be 10. And so those values should make sense from that conceptual standpoint. Everybody with me so far? Now, if you're with me, then somebody tell me what is the area of shape 1? Yeah, 38.5. Yeah, so I got 38.51. I don't know that really matters, but you're exactly right. What about area here? -36.5. Exactly right. All right. So this is positive 38.51, negative 36.51. Let me stop my share for a sec because I want to show y'all something. Okay, so here we had 5 regions. So area 1, area 2, area 3, area 4, area 5. Okay, these are the 5 areas that we came up with. Okay, so what I want to do is I want to take these areas and I want to determine the positive area and the negative area. And so the way that I'm going to do that is I'm just going to add up all the positive numbers, add up all the negative numbers. So for the positive numbers, I've got, what is that? I've got area 1, area 4, and area 5. Okay, and so 100, and that 238.51. Or 52. Yeah, I'm sure there's probably a little bit of rounding issue. That's really no big deal. Now, what about the minus areas? Well, the minus areas, I'm going to do this and this. So area 2 plus area 3. And when I add that up, I get, what is that? Minus 258.51. Dagnabbit, they don't match, right? So this is what was going to happen, right? They don't match. So area positive and area negative doesn't match. So how far off are they? What's the difference? So we have 258 and 238, and the difference, just from a magnitude perspective, is 20. Why did the difference come out to be 20? Because that's how much our concentrated moment was, right? When you go to the original problem, actually, let's just do this. When you go back to the original problem, look at the moment. The concentrated moment is 20, okay? And so the difference is that 20. Now the question becomes, do we make that 20 a positive moment or do we make it negative? Well, if I make it negative, I'm going to have, so maybe I'll put this on the screen. So area positive is 238.51. Area negative is negative 258.51. And so the question becomes, do I make that 20 moment? I guess it's not do I make it, it's whether or not it is. Is it a positive bending moment or is it a negative bending moment? Well, I propose it's a positive bending moment because what I need to do is I need some extra positive area so that these balance out. See, if I put minus 20 here, what's going to happen is I'm going to have 238 of positive area, but 278 of negative area. That 20-foot kip moment is a positive moment. So it's going to cause a vertical jump in the shear diagram. And if that is a little fuzzy, let's just draw the moment diagram and let's see what happens. Okay, so, oh goodness, that got away from me. Oh, why is it doing that? Let's do this. Apologies for the scrolling around. That's getting a little crazy. Okay, so okay, so here's the bending moment diagram, and again, we're going to start at 0 and hopefully end at 0. And remember, if all we did was follow the areas, we wouldn't start at 0 and end at 0. We'd start at 0 and end at like -20 or something. So we'll start at 0. And now what are we going to do? Well, first thing we probably need to do is we need to take this line here and sort of extend it down a bit so that I can see what's going on. So let's start off with this this region here. Okay, so let me blow it up. This is 0. So option 1 is, okay, so we have a linear shear diagram, so we're going to have a parabolic moment diagram. So option 1 is that it does that. Option 2 is that it does that. So this is option 2. This is option 1. How many people think it's option 1? How many people think it's option 2? Exactly right. That's what I like to see, option 1. So it's going to go like that. And I apologize for that being wavy like that. I don't know why it's doing that. Let me see if I can do a little better. That's about the best you're going to get out of me. Now, how far, what's that value there? What is that value? 38.5, exactly right. So, exactly right. So, 38.5. Now, if I'm at 38.5, 38 or 38.51, whatever, and I drop down 36.51, what's that going to put me at? That put me at like 2, right? So, let me see. I guess maybe right there, just right above the line. Okay. Now, make sure everybody's paying attention. Option 1, option 2. That's option 1. That's option 2. Which is it? 1. Exactly right. That's what I like to see. So we're going to do like that. Boom. Right. Marker drop. All right. Now, so this is 2. Okay. These microphones are expensive. I'm not dropping the microphones. Okay. So I'm at 2. So what am I going to do from here to here? What's it going to look like? So it's going to drop down.
It's going to be a linear line heading down to -222.
Well, hold on. It's not going to drop to -220. We're at 2. And so if we drop down -222, what's that put us at? -220. So you're on the right track, but yeah, we're dropping to -220. That little 2, that'll matter at the end.
Yeah.
It's going to drop.
I missed the 2 there. Sorry.
What was that?
I missed the 2.
No, that's fine. It's really tiny. I know it. It's kind of hard to see on the diagram. But yeah, that'll drop down to -220. Okay. Now, then what do we do from here to here? Well, it's going to be a line, but it's going to be positive, right? Let me rewrite that because that looks like 210. It's 220. -220. Okay. So we're going to come up. Now, I just want to go just to this first line. I don't want to go all the way to the very end. So if I'm at 220 or negative 220 and I go up 100, that puts me at negative 120. So it's going to look like that. So that's negative 120. And that's a straight line. I know that probably doesn't look the greatest. Let me see if I can do a little better. Okay, so straight line. But then what happens there? What happens at this particular point? Well, at this point, we've got that concentrated moment. So we jump up 20. And so if I'm at negative 120 and I jump up 120 or jump up 20, that puts me at negative 100. And then the positive 100 is going to bring me back home. This is negative 100. Okay, I heard a Mr. X.
So how do we determine if there's a concentrated moment in the beam? How do we determine if it's a positive or a negative? Is it how it's...
That's a great question. And to me, the simplest answer is to look at your areas, okay? If you look at your areas, okay, remember the areas have to balance out, but they're not balancing out, okay? And they're off by a value of 20. Now, we agree on that just by looking at the math. And so the question becomes, where do I put that 20, okay? So let me pull up my board here. Okay, so we have a positive area of 238.5, let's just do that, and a negative area of negative 258.5. If we treated that moment as negative, then this would be 238.5, but this would go up, this would increase by a magnitude of 20 to be 278.5. That wouldn't make sense. That wouldn't bring us closer to equilibrium. That would bring us further away. And so the only way of handling this is to increase. So instead of decreasing this by 20, we need to increase this by 20. So this would be 258.5 and then minus 258.5. So that means that moment has to be positive. So you have to jump up. And that's one way of doing it. Another way of doing it is to try and look a little bit into the crystal ball. If you look at the problem, okay, go back to the moment diagram and then ask yourself, like right here, what would have happened if we took that moment and jumped down? Well, if we jumped down, if we went down and then went over, we wouldn't be anywhere close to zero. Does that make sense? So there's a couple ways of going about it. I think those are sort of the easiest ways. I'll erase all this. All right. Any other questions? Okay, well then let's go ahead and just handle the next one. All right, so this is example 5. Again, we've done this example before. So this example was a cantilevered beam problem. Now there was an inclined load with this problem, and that doesn't really make things complicated, but we do need to handle that inclined load. Remember, you can take that inclined load and split it into the X and Y components. The X component, because remember that's a 3, 4, 5 triangle, the X component is going to be 3/5 of 10 kips, which is 6 kips, and then the Y component is going to be 4/5 of 10 kips, which is 8 kips. Okay, and again, this is a problem that we've done before. Okay, now the one point that I would mention is that that whenever you're drawing a shear diagram, and we actually had a homework problem on this, so this isn't all that complicated, but when you're drawing a shear diagram, the only thing that contributes shear for a beam are your vertical loads. I mean, that's one of the reasons why we use the letter V for shear, because we're talking about the change in vertical forces. So just you know, a little tidbit there. Now what we're going to do is we're going to handle this problem the same way, but we're going to find the same issue with the area problem. In fact, it's going to be even more magnified. So I want to draw the shear diagram and moment diagram for this beam. And again, it's not going to be anything confusing or anything all that complicated. It's going to be pretty straightforward. So let's start off with the shear diagram. I think that's like the straightest line I've drawn this entire semester. It's not going to be any better than that. It's just going to get worse. Okay. Actually, I'm going to need to go a little bit up. That's good enough. That's good enough. Okay. And so, again, when you're drawing a shear diagram, start at 0 and you just track your vertical load components, okay? So the first thing that we see, we start at 0, we suddenly jump up 28. And then from A to the middle of the beam, nothing, no change. And 28. And then what do I do here? Okay, well, I drop down. How much do I drop down? I'm asking you, how much do I drop down? Is it 10 kips? No, it's 8 kips, exactly, the vertical component. So I'm at 28, drop down 8 to 20. Over to 20, drop down 0. Exactly straight, you know, starting and ending at 0 should be pretty straightforward. Now we need to determine the area of each of these rectangles. So over here on the left, it's just going to be 28 times 10. So that's positive 280. And then over here, positive 200. Okay. Everybody with me so far? All right. The moment will have to be negative. That's exactly correct. Okay. Well, the concentrated moment reaction at A. See, if you look at all of your positive area, you're going to have 280 plus 200, which is 480. But the negative area is 0. See, there is no negative area on this shear diagram at all. So this is what I was talking about while I was like, your area problems are going to get even worse with a cantilevered beam. But remember, what do you got here? You have a 480-foot kip moment right here at A. So, oh, man, that got away from me. So the first thing that you're going to do, well, first I got to set this up first. You start at 0, you've got this 480-foot kip concentrated moment at A. What is that going to do? It's a sudden drop, and it's a sudden drop downward. You say drop, well, you're not going to drop down 452, you're going to drop down 480. But you're correct here, minus 480. And then it's just going to be 2 straight line segments. It's going to be a straight line segment. So the total area is 480. So you know you're going to end at 0. So you're going to come here, straight line, and then here, straight line. Anybody tell me what that point is? Negative 200. That is correct. Because you're at negative 480 and you jump up 280, so that puts you at negative 200. And so that's your moment diagram right there. I want to show you all something before we call it, because I've got a physical example that I want to illustrate for you here in a second. I'm going to give everybody a sec. I want to see if anybody has any questions. All right. Before we end off, I want to show you a couple things because this is kind of important. So first off, I think it was right here. So yeah, this is examples 5 and 6 in the reaction side of things. And if you look, you can see here's the math that we did to determine those support reactions for these beams. So right off the bat, if you ever have any questions like, well, how did he get those values? They're right here. And remember, if you go into course content in the notebook, you can review all these calculations. Okay. Now, I want to talk a little bit about what we got as a result, like, and what does it mean? Okay. Because, you know, we've got this shear and moment diagram, but it's like, what does it mean? Like, okay, I've got this moment diagram and it just looks really strange. Like, you know, it's this, you know, weird blob looking thing. Like, what is that? How do I interpret that? The easiest way to interpret that is to actually, let's start off by looking at the cantilevered beam, okay? One of the things that you'll see in the cantilever beam is that if you look at the moment diagram, all of the moments are negative. So this moment diagram is completely negative. What does that mean? Okay, well, let me show you something. I have here my mock beam set up, and let's say for the sake of discussion that this is the clamped end. Okay, so this is the fixed end, and there are some loads that are like right here and right here. Okay, now here's the clamped end, and imagine that there's loads here and here. What is this beam going to look like when it bends? Okay, it's going to bend kind of like that, right? This is what it looks like when it deforms. Now, right now, we don't know how much it deforms, right? That's going to be the topic after exam 1, is to actually compute, like, what is that deformation? Like, delta equals what? Or rotation equals what? That's going to be the whole topic after the first exam. But for the sake of discussion here, just I think we could probably all agree that it's bending downward, okay? And if you turn that around, kind of looks like a frowny face, doesn't it? Kind of looks like the beam is frowning at you. Whenever you have a moment diagram that is negative, okay, that corresponds to the beam's deformation being down in nature, okay? So if you go back to the notes, okay, if you go back to the notes and you look at this moment diagram, that entire beam, oh goodness, okay, that entire beam has a negative moment diagram, so the entire beam is deforming downwards. I'm not making you do it on this homework assignment, but we might look at it later. If you open up the textbook, one of the things that the problem or the book is asking you for is to draw the qualitative deflected shape. Now, I'm not asking you to do that right now because there are some other rules that you would need to understand to effectively draw that. But for the sake of like a simple discussion, that entire beam is going to be deflected like that. It's going to be deflected downwards. Whereas if you look at this beam, what is this beam going on? Well, most of the beam is going to be frowning at you, but some of it isn't. If you look at the leftmost portion of the beam, that left portion of the beam has a positive bending moment. So that's the beam bending like this. It's smiling at you, okay? So, you know, these bending moments also, they're reflective of what's going on physically on the beam in terms of how it responds. Now, this smiley face, frowny face bending, why does that matter? Like, why does that matter to the structural engineer? Who cares whether or not the beam is smiling at you or frowning at you? Well, it matters substantially from a design perspective, okay? Let's take the instance of reinforced concrete design, okay? Now, one of the things, if you all decide to take reinforced concrete design, one of the things that I, sort of hammer into your head is that concrete is a material that behaves very, very well when it is subjected to compression. But when it's subjected to tension, the concrete beam tends to want to crack. Concrete's a material that's weak in tension. The reason why we put rebar into concrete and create reinforced concrete is because we want the rebar to increase the beam or the element's tensile capacity. That's where, if you understand that, that's like reinforced concrete design in a nutshell. And so a really simplistic way of looking at it would be if I was looking at this moment diagram from, let's say the beam is rectangular. Like, let's say here's the beam. Okay. If I'm looking, let's say, in this region of the beam, I probably need the rebar in the bottom, right? But if I'm looking at this region of the beam, I probably need the rebar on the top. I need the rebar on the top layers of the beam, because that's where, think if the beam is smiling at you, then the bottom is experiencing tension, so I need the rebar on the bottom. If the beam is frowning at you, I need the rebar at the top, okay? And that would be the implications in concrete design. In steel design, there are similar implications. When you have a beam like this, hold on, I'll see if I can show you on the screen because it's a little easier here. When you have a beam that's like this, okay, let's say for the sake of discussion, it's smiling. If you take this beam and you bend it, what happens is the beam kind of experiences this strange phenomenon where it wants to kick out and twist. Like it kind of, I don't see if it's kind of hard to see, but it kind of like kicks out and twists like that. And the beam's capacity is largely determined by how strong the flange is, the one that's in compression, okay? So if the beam is smiling at you, I need to make sure that the top flange has that buckling capacity. But if it's frowning at you, I need to make sure that the bottom flange has that capacity. So like in bridge land, if you have like a bridge, let's say, here, let me erase this real quick. So let's say you got, I don't know, a road here, you've got a median, and you've got a bank here, and a bank here, right? So here's your bridge. Land sounds like a fun amusement park. I enjoy it. That's me. So here's the bridge, right? And here's the underpass. Here's the pier on that beam, and so there's the head of that pier. Here's the abutment that the bridge sits on. Here's the abutment that the bridge sits on. Okay, and so here's your bridge. Okay, well, when you put a lot of load on the bridge like this, just to keep the discussion simple, if you draw the moment diagram for this, which, by the way, the moment diagram for this if this is a continuous beam, then this is an indeterminate beam. So I don't expect you to have to draw this. So don't worry. But if you draw the moment diagram, what it looks like is it kind of looks like this. It kind of goes up, then it goes, then it goes like that. And that's kind of what the moment diagram looks like. So in this region right here around the pier, the bridge wants to bend like frowny face. But here in the main body, like here and here, the bridge wants to smile at you. So, it's all about determining which of the elements are in compression, which of the elements are in tension, and then depending upon whether or not you're in steel design land or concrete design land, that tells you what you need to know from a design perspective. So the sign for your moments is incredibly important. If I'm being honest, the sign for the shears doesn't really matter all that much. You need to keep your sign convention to ensure that the math that you're doing is done correctly. But whether or not a beam is experiencing 70 kips of positive shear or 70 kips of negative shear doesn't really matter in the end, because it's just about whether or not it's being sheared like that or being sheared like that. Whether or not I look at it this way or look at it that way, it's still the same effect. So the sign convention for shear doesn't really matter much from a design perspective, but moment, big deal, big deal. How long will we have for our celebration? Have you been waiting all this whole time to ask that? My goodness. So I'll tell you what I did in I'll tell you what I did in statics, and it seemed to work out well. There was no issue from a timing standpoint. What I did in is the exam was an hour long, so I had an online quiz on Blackboard, and so we'll use the times in here so that it's scaled over. So the quiz will open like at 10 a.m. and it will close at 11 a.m. So you'll have 1 hour to do it. You'll quiz on Blackboard, but then later on you'll upload and submit a PDF. And what I did in statics is I said, just get me the scanned PDF of your calculations by, I think it was like 11:30 or noon or something like that, because I don't want you to be freaking out. Well, not only do I have to take the test, but I have to break out the cam scanner and scan my phone and send it. Oh, I don't want you to be crunched on time for that. Just do the exam and upload your calcs later is kind of the idea. Now, I'll say one other thing. Whenever I build an exam, I always operate off of what I call the rule of 3. And so this is what I did for statics. Once I made the exam, I did the exam. And the idea is if I do the exam in 20 minutes, then you should be able to do it in 60 minutes. And I've always adopted a rule of 3 on that, and that's usually helped ensure that the exams aren't too long. I don't really had too many issues on that in statics from the exam being too long, nor have I had issues since I've been teaching structural analysis. I've always used that philosophy. It's never been an issue on time. I'm not going to create an exam that's going to take hours and hours and hours to do. I don't like it when you're given an exam that takes 6 hours to complete and you only have 50 minutes. It's not a test of your ability to perform structural analysis. It's a test of your ability to do this really fast and hit buttons on your calculator really fast. So I don't want it to be a time crunch. But what's most critical is that you understood what we did today. Y'all got homework to do on Wednesday. Are there any more questions? Mr. Romans is good. Everybody else?
Yeah, I'm good.
Good deal. All right. Well, homework's due Wednesday. On Wednesday, what we're going to do is we're going to handle the final topic with beams, which is how to deal with an internal hinge. And the short answer is you don't deal with it. If you do your reactions correctly, then everything works out in the end. So you actually don't really need to do anything with the hinge. But we'll do one final problem that kind of ties a bunch of stuff together. Friday, we're going to handle frames, but we're not going to put that on the exam because there's really nothing to frames. It's just moment diagrams and shear diagrams like that. But the concepts are the same. And then Friday, we'll talk a little bit about virtual work, which is going to be a really important topic after the exam. But that's all I have, everybody. I will see you all on Wednesday. Y'all have a wonderful day.